All right, guys. So we have been doing Riemann sums. We have been finding area under the curve using LRAM, MRAM, RRAM, and trapezoids. And today we finally see, what this little integral symbol means besides area under the curve, the exact area. So I have here, it says we're going to do a proof. And it says here that if I take the derivative of this elongated S, that I just get whatever I have on the inside. See, that's all it says. So what does that mean? Like, okay, so it means, so let's do an example. d dx, integral, and I can make any constant on the bottom, and as long as I have an x on the top, and I can say 4t squared dt, and this is considered my f of t, see? So if I take that derivative, that just means that I can just switch the x and the t, and I can call that 4x squared. So that's all it means. It says derivative of this elongated s, or this integral here, is just 4x squared. We're going to do that proof of y. So here's the proof. So bam, bam, all this is part of your proof. See what's going on. And then they tell you that they have some little piece there. And then the proof continues on the next page where they're taking a derivative. And then here it is for some c between x and x plus h. And you get f of x. And it says this concludes the proof. Did all that proof make sense? No? Okay, no, we're going to go ahead and do it with pictures. So here it is. This is actually the fundamental theorem of calculus. Sometimes they call it FTC, or maybe it's preferred FTC instead of FTOC. All right, we're going to do this proof right now. You guys ready? All right, so go to this picture here. So it starts with a capital F. They're just calling this capital F. What do we know about this? Well, we know that this means exact area. So according to what we know, here it is. I'm exaggerating quadrant 1. I'm going to call this f of t. I'm going to call this lower limit a. And I'm going to call this point x. And I'm going to say that this means this, area between a and x. Does that make sense to you? I'm going to call all that area capital F of x, because that's what it says. I'm going to get another color. And if they call this f of x, I'm going to go f of x plus h. All I'm doing is, look what it says here, guys. If they have an x there, notice that the x is up there. So if I had a happy face in there, then I would have a happy face up there. So, some constant elongated, a, my upper limit, x plus h, and it's still the same function, f of t dt. What does this mean in terms of pictures? Well, here's x, so I'm going to say h is like right here, or x plus h. So, boom, boom. And this in blue is f of x plus h. So that means this point here is x plus h. So this gap in between must be h. Have I done anything crazy? No, I haven't done anything crazy. This point here is what I really want. I want that point. That is just some f of x. Just like this point is some f of a. Bless you. Have I done anything crazy yet, guys? No, right? If I took the area in blue and I subtracted the area in red, do you see this rectangle that I would have? I'm going to use LRAM. Notice I'm using LRAM. So that's exactly what I'm going to do. I'm going to take the area in blue. So the area in blue is the area from a to x plus h of f of t dt. And I'm going to subtract the area in red from a to x of f of t dt. And I'm going to have the area from x to x plus h of f of t dt. Let me make sure that I am following along with the proof here. Yeah, I'm right here at that moment. I haven't used the lower limit yet though. Okay. Yeah, they're all. Those are not capital F. Those are little f's. But this, yeah, we're about to use that capital F in a little bit. I'm just following the proof, trying to make sense of it. So hopefully you guys are understanding it. Does everything make sense so far, guys? Okay. All right. You okay? This expression here, that was just capital F of x plus h. Minus this expression here, that was just capital F of x. And I want the area under that curve. So it's approximate because we're using LRAM, right? It's not exact. It's a rectangle. So the area under that curve is approximately, let's see, x plus h minus x. So that's going to be h times LRAM. So the height of that rectangle is f of x. Does that make sense so far? Okay, where did I lose you, Salali? I just got it from width times height, h times f of x of the rectangle. Tell me where you're lost, miss. F of x is just some y value, but if we're up to here, we're okay, I think. Salali, do we get it all so far? All right, check it out, guys. I'm going to go ahead and divide everything by h. Chav, why are you doing that? Because I noticed that on the left-hand side, this is starting to look like something very familiar to us, I hope. Capital F of x plus h minus capital F of x all over h is approximately f of x. But I do not want approximate. I want the exact. The only way to get exact, I'm using LRAM, right? Do you agree that if I make h approach 0, this will be right at f of x? Yeah, look. If I make h approach 0, guys, if I make h approach 0, if h is 1, that's x plus 1. But if x is 0.5, then I'm right here. If x is 0, I'm right on x, and that's a perfect f of x. You guys see that? So I'm going to use, Chop, what are you trying to say? I'm going to use a limit to get the exact, because I want exact. So I'm going to go limit as h approaches 0 of capital F of x plus h minus capital F of x all over h. Now this won't be approximate anymore. It will be exactly f of x. Here comes the beautiful part. Are y'all ready? This that I'm circling, what does it remind you of? It's just a derivative. The derivative of capital F. And what this is saying is that the derivative is just little f of x. So Chop, what does it mean in conclusion? Guys, look what capital F was. Capital F was this elongated s, this integral from a to x of f of t. So that means I can say d dx, elongated s or integral symbol from a to x of f of t dt is nothing more than f of x. That is called the fundamental theorem of calculus. Sometimes they give it a name, part 1. Sometimes they don't put the O. Chav, at MIT they say FTC. It's the same thing, guys. Cool or not cool? Oh yeah, we're going to use it right now. F of x, yeah, so we're just saying that it's just whatever you have on the inside, you just change the letter, right? That's all it's saying. As long as I'm taking a derivative. So Chop, how do you use it? Okay, here it is. Here's some examples, guys. You guys ready? I have d dx on the outside, so that means I'm taking a derivative. Do I have a constant at pi? Do I have a constant in my lower limit? Do I have a variable at my upper limit? Yes, yes, and yes. So according to my fundamental theorem of calculus, check it out. I'm looking at my fundamental theorem of calculus right here. According to my fundamental theorem of calculus, So this is what I'm looking at. I'm looking at the cosine of t. This will just turn to cosine of x, if you want to put a parenthesis around the x for your argument. And that's it, you're done. Cool or not cool? All right, here we go. Another one, guys. All I'm doing is this, miss. I'm just following this. d dx, I have a constant, I have a variable. F of t dt is just f of x. Change the t to an x. That's all I'm doing. Just following my... Do I have a constant in the bottom? Do I have a variable in the top of my integrand? It says d dx. Wherever you have a t, change it to a 1 plus 1 plus x squared. Or 1 over 1 plus x squared. Cool or not cool? All right, check it out. Next one, chain rule. I'm still taking a derivative. Notice they call it this time, they call this a y. They want me to find dy dx, so they want me to find the derivative of this. I still have a constant in the bottom. Notice in the top, I don't have an x, I have an x squared. So you have to do chain rule. And if you think about it enough, you were doing chain rule here, but the derivative of x is just 1. So here it is. So what do? The same process, y prime equals, I'm taking the derivative of this. The integral symbol goes away. Wherever I have a t, I plug it into whatever I have there. You're going to go cosine of x squared. Because I had a t in there, see? And you're not done yet. What's the derivative of x squared? Times 2x. You're taking the derivative of x squared, the upper limit. So, making it nice and pretty. 2x cosine x squared. How are we feeling, guys? Okay. I don't know why I put so much white space there. I'll adjust it next time. Go to example 3. I want the derivative. Notice I have a variable in the bottom limit, and I have a constant in the top limit, in the top upper limit of my integrand. It's in the wrong order. I need the constant in the bottom and the variable in the top. There's a property, we just learned them a few days ago. If I switch them, what do I put in the front? So this expression, I haven't taken the derivative yet. I'm just going negative integral 5 to x of 3t sine t dt. Are we okay? Here we go. Y prime equals negative. That negative is that negative. 3, and then instead of writing t, I'm going to write x sine x. There it is. You took the derivative of that integrand. Done. Next one. Okay, check this one out. Variable on the top, bottom, variable on the top. I cannot do a derivative right off the bat. I can't. You need a constant in the bottom. So the first thing you're going to do, I'm going to write side notes because I need you guys to remember this. So here's A. This is a side note, guys. This is all a side note. Here's B. Here's C. D, and I'm going to call this f of t. So area under the curve. Area under the curve from A to B of f of t dt. Plus, wherever this one stops, this one begins. Integral from B to C of f of t dt. Do you agree that that is area under the curve from A all the way to C of f of t dt? That property is that's what I'm gonna use. See where this one stops, the other one better begin, and that will give me all of this. That's the same thing I'm gonna do with this one, guys. Chab, what do you mean? Here's what I'm gonna do. Integral 2x and pick any constant. You can actually just use a letter if you want, like A, but let's not use a letter. Give me a number, any number. 5, I heard a 5. That's our AP square that we want. 5 of 1 over 2 plus e to the t dt. This function is continuous everywhere. It doesn't have any vertical asymptotes. We'll talk later on about when, okay, you know what? We're not in BC calculus. Well, you guys are, but we're not there yet. Plus integral, where this integrand stopped, the other one better begin. So what do you think I'm going to put it for my lower limit? 5, and then my upper limit of 1 over 2 plus e to the t dt. I am ready. Here we go. This, what am I ready about? I'm ready to take a derivative. What kind of? This one right here. Actually, this one's right. This one right here. This one right here, I need the lower limit to be a constant. So I'm just rewriting it. Y equals negative in the front, integrand from 5 to 2x, 1 over 2 plus e to the t dt, plus, and then this one I leave alone, 5 to x squared, 1 over 2 plus e to the t dt. Now I'm ready. All right, I'm going to write y prime equals. So now I'm taking a derivative. Wherever you have a t, I'm plugging in the expression 2x. 1 over 2 plus e to the 2x. I'm not done, chain rule, times, what's the root of a 2x? 2. Plus 1 over 2 plus e to the x squared times, what's the root of the x squared? 2x. Making it nice and pretty. Let's see, I don't see any issues. Oh, there should have been a negative here. That negative is that negative. I knew something was off there. Negative 2 over, let me put the negative next to the 2 there, over 2 plus e to the 2x plus 2x over 2 plus e to the x squared. There it is. That's my derivative. What do you guys think? Yeah, yas. Yeah, sorry. You guys okay? How's the energy? How's the vibe? You guys passed the vibe check? Oh. All right, let's read what Theorem 4 says. Look, it's still fundamental theorem of calculus, part 2. Some people name it. If f is continuous at every point on AB and f, capital F, is an antiderivative of f on AB, then, so this is an antiderivative of f. The part of fundamental theorem is called the integral evaluation theorem. Okay, guys, let me rewrite this because I think, not that I don't think you guys understand that. I think you guys understand it. But here, you guys will figure this out easier. A to B, f prime of x dx equals f of b minus f of a. There it is. Upper minus lower. F prime, and then if you go backwards, antiderivative of f prime is f. That's what they're saying. That's what it's saying. All right. Let me help you understand. Okay, guys. This is a big deal. Do I have, I wish I could scroll back up. That's fine. I'll just say it. Don't look at that f prime. Is there a ddx here in the front of this integral? No. So remember when we did, I just want you guys to remember, when we did have a ddx in front of that integral, look what happened. Well, I guess all that happened, but where's my little formula? I guess I put it over here. Look what happened. ddx of this integral gave me that function. Now if you take away that function, if you take away that ddx, well then obviously that integral must mean antiderivative. I took the derivative of something and it gave me the inside. So if you take away that derivative, that something on the inside must mean antiderivative. That symbol that elongated S. Does that make sense? Yeah, let me reword it because maybe my English is bad here. I took a derivative of this weird symbol and it just gave me that inside. Okay, if I erase that derivative, that weird symbol must mean antiderivative then. Does that make sense, guys? That is what fundamental theorem of calculus part 2 is. I wish they would have written it like this because I think it's easier for you guys to understand it like this. See, there's my f prime. Oh, look, what does it mean? F of b minus f of a. Where does that dx go? Guys, it's part of the theorem. That dx, you need it. You got to have it in there because remember, we're adding an infinite amount of rectangles. That's all you're doing. So you always need that dx. That's that delta x times height. Delta x times height. An infinite amount of them. But there it is. Antiderivative, upper minus lower. So here it is. I wrote it for you guys again. And we're going to show you how to do it. We're going to go slow. All right. Especially if you have more than two terms. You always need that dx there. You guys ready? -1, 2, 3. Okay. Fair warning. Some textbooks, relax. Some textbooks will write it like this. It's understood that the f of x is always in between your integrand and the dx. So it's understood. Like this is kind of like your start. So then you have your expression. And then as soon as you see dx, it ends your expression. So it's understood. Whether you have the parentheses or not, it's understood. It's like width times height, width times height. Does that make sense to you guys? Okay. All right, here we go. I'm going to put the parentheses in there. I'm going to go equals. What is the antiderivative of x cubed? Antiderivative, guys. Just go backwards. You've done it before. Add 1. X to the 4 divided by 4 plus what's antiderivative of x? Just x. Did I say antiderivative of x? Antiderivative of 1. Sorry. Yeah, 2 terms. Yeah, antiderivative of 1. Sorry. Antiderivative of 1 is just x. You have 2 terms. I put them in a bracket. I put the lower limit -1. I put the upper limit 3. This is the correct notation. Sometimes you'll see this. Okay, let me erase this temporarily. Don't worry, you're correct still. Sometimes you'll see a line that just means evaluate at -1 and 3. You computer scientists have probably seen it like that, because that's how you tell. Okay, I'll stop talking because in case I don't want to confuse you guys in computer science. But it's perfectly okay to do this. And then I can go equals, and look what it said, upper minus lower. So you're going to do the 3 first, giant parentheses, 3 to the 4th over 4, plus 3, close, minus, open parenthesis again. I'm plugging in the lower one. -1 to the 4th over 4, plus -1. Did I confuse anyone? Okay. And now I'm just going to type it. Let's see, 3 to the 4th, 3 times 3, 9, 9 times 3, 9 times 9, 81. 81 over 4 plus 3. That's in my first one. Minus -1 to the 4th. 1/4 minus 1. Yeah, maybe it's faster if you just type it in the calculator, but I already started, so too bad. All I'm doing is arithmetic, guys. I'm not doing anything else. Yeah. Lower limit is A, upper limit is B. Minus 1/4 minus 1, -3/4. All right. 81 plus 12. 81, 91, 92, 93. Dang, I messed up here. It's not a big mess up. That should be a 4. 12 divided by 4 is 3. Okay, now we're good. 81, 91, 92, 93. 93 over 4 plus 3/4. 96 over 4. 25 times 4 is 100. So 24 times 4 is 96.
Just 4?
Yes.
Sorry, it had to be 16 on top. Just 24.
I'm going to erase that. Well, I have no idea why I put 4. I can't believe I did that. Man. I can't believe I put 96 divided by 4 was 4. Oh, that's so funny. All right. And no one even questioned it until afterwards. I didn't do that in first period, did I?
No, you counted 25 and 100 minus 4.
What did I do that I wrote 4? Okay, I'm just tired. All right. I don't see any issues now. Yeah, 25 times 4 is 100. So 24 times 4 is 96. So yeah, the answer is 24. Okay. Chavez, I found that integral symbol in the calculator. Can I use it? Sure. You're in the calculator section. Super AP stands well. Calculator. So how to use the calculator? Okay. So take your calculator. Only use it to check your work, especially because I know some of the. You're gonna eventually have a UH quiz on this. Yes, I know that the calculator can do it, but try try really hard not to. All right. So if you have your calculator, go ahead and try it, guys. Take your calculator so you guys can try it with us. All right. Push the math symbol. Scroll down until you see something called FNINT. That's function integral. See this? Type in this one. -1 to 3 of x cubed plus 1. -1 to 3 of x cubed, x to the third power, plus 1. Was it -1? Let me check. It's +1. It's +1. Man, miss, you got me all tripped. 24. And there it is. Don't use this just to use it when we're doing the UH and the delta math. Use this to practice. You gotta sweat a few times, guys, because if not, remember 60% of the exam is with no calculator. You're gonna get to the no calculator section. You're gonna be like, oh, where's my calculator? Okay. All right, we're just practicing. Let's. Oh, I love this question. Okay, we're almost done. Last page. This is the type of question you had yesterday when you were doing your mock exam. I thought it was too early to give you a mock exam in February, but it wasn't up to me, guys. All right, check this out. Use the graph of f to analyze h of x equals that integral symbol there. The graph of the continuous function f with domain 0 to 8 is shown to the right. So this is f. Put f. Let h be the function defined, and they tell you how h is defined. We still okay? It says, first letter says, find h of 1. Okay. H of 1. Integral 1 to 1. All right, check it out, Pina. We're going to do the letter that we didn't do earlier today. I don't know why this morning. We should have just done it. From 1 to 1, have I moved? So this is going to be what? 0. Done. Is h of 0 positive or negative? Well, I don't know. Let's see. H of 0 equals integral from 1 to 0 of f of t dt. I start at 1 and I end at 0. So, no, but we didn't do letter D, I think. Is this positive or is this negative? Hey, can you close my door, Pina? Yeah, it's negative because you're going backwards. You could also, if you want, like, oh, I don't want to go backwards. I want to go from 0 to 1. Like, you could switch the limits, but if you switch the limits, you got to do what? Put a negative in the front. Negative, and look, 0 to 1 of f of t dt. See? So it's negative, and I'm going to write, what am I going to write? I'm going to put the area under the curve from x equals 0 to x equals 1 under the curve caret of f of x from x equals 0 to x equals 1 is positive. But, I already said but since the integral starts at x equals 1 and stops at x equals 0, comma, integral from 1 to 0 of f of t dt is negative. That's how you say negative in math. Does that all make sense? Let me see if it makes sense. The area of the curve of f of x from x equals 0 to x equals 1 is positive, but since the integral starts at x equals 1 and stops at x equals 0, the area of the curve from 1 to 0 of f of t dt is negative. Is that how we said it earlier, Pina? How did we say it? I felt like I said it better in first period.
Area under curve from x equals 0 to x equals 1 is positive, but the integral starts at x equals 1 and ends at x equals 0. Hence, what's that?
Hence, the integral is negative.
Yeah.
I wrote it better in the morning. Here, hook me up with yours. I'm gonna say yours. I don't know why sometimes I do it better. I guess I'm just getting tired. I wrote area in the curve from x equals 0 to x equals 1 is positive, but integral starts at x equals 1 and ends at x equals 0, comma, hence, and then I put this. Hence, integral from 1 to 0 of f t dt is negative. That's fine. Maybe the hence word made the difference. Who knows? Cool or not cool? All right. The same rules still apply for letter C. Find the value of x for which h of x is a maximum. Where do you have a maximum? Whenever what changes from what to what? When what changes? When the derivative changes from? All right, well, check it out. I can use FTC. So I'm going to write h of x equals integral from 1 to x of f of t dt. So then I'm going to write h prime of x. That's my derivative. What's my derivative of that? Yeah, f of x. So what you're looking at right here that says f, you can write f equals h prime. This is my derivative graph. Well, for h, it's not the derivative graph for f. But for h. Does that make sense? So because that's a derivative graph for h, where does h have a max? At what number? At 4. No, we're almost done. No yawning. That's at 4, guys. So there it is. So I'm going to write h of x has a max at x equals 4 since h prime of x equals f of x changes from positive to negative at x equals 4. Full credit. I didn't do letter D with the morning period, guys. I should have. I'm going to do it right now. It says find the value of x for which h of x is a minimum. And it's because I don't like to talk, well, anytime you're finding extrema, you should always consider your endpoints. But usually they're talking about like your critical. Okay, let's just talk. Think about the graph h, not the graph of f. It says h. Yes, I know that h has a minimum whenever the derivative goes from negative to positive. That doesn't happen here. Your derivative never goes from negative to positive. It's either positive or it's almost right there, see? So what you got to think about is this. My only two candidates are the endpoints. At x equals 0 is a min, and at x equals 7 is a min. Now, which one's the lower value? So you got to think about it. So let me go over here real quick. So think about h. Think about h. So h, it starts going up, going up, going up. I have a horizontal tangent at 1. Going up, going up, going up, going up, going up, going up. So at x equals 4, that's definitely the absolute max. And then going down, 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 all the way till I got over here at 8. So remember, we're only considering the endpoints as a min. Child, how is x equals 0 a min? Think about it. You start and you immediately start increasing. Going up, going up, going up, going up. So x equals 0 is a candidate for minimum. That is a min. What does the exact wording say? What does the wording say? Absolute min or find the value of x or x is a minimum. Okay. So let's be specific. I have a minimum at x equals 0, and I have an absolute minimum at x equals 8. Both of them are minimums. That's a relative minimum. Now, our textbook has relative minimum and an endpoint, but that's definitely an absolute min. Child, how can you tell? Look at area under this curve and look at this area. This area below the x-axis is bigger than the area above the x-axis. Child, I don't understand. Okay. Let me give you a scenario. Imagine this is velocity. I start at a position, I move right, stop for a moment, move right. This is the furthest right I'll ever be. Then I move left, move left, move left, move left, move left, move left. When I stop, I am way further to the left than when I started because I moved more to the left than I moved to the right. Does that make sense? So absolute minimum at x equals 8. So let me write that down. 6, 7, 8. Absolute min at x equals 8. And then I'm going to say relative min. Relative min at x equals 0. And then I'm going to put some textbooks will not recognize x equals 0 as relative min. Ours does. I want to say most professors will say yes to this, but depending on who you ask, depending on what textbook you have, they don't consider endpoints for relative. They only consider endpoints for max, absolute max, and min. Okay, that's why I didn't want to talk about it. Does that make sense, guys? Or no? Okay, last one. You guys okay? Do we still got energy? No? One more, guys. Find the x-coordinates for all points of inflection on the graph of h. Where does h have a point of inflection? Whenever what is increasing or decreasing? Yes, this is the graph we have. Remember, point of inflection happens when the second derivative changes signs. I don't have the second derivative. Well, I guess not directly, but I have h prime. Wherever h prime has a extrema. So I have a point of inflection, so I'm going to write h of x has points of inflection at x equals, what's my first one? 1, comma 3, comma, and what's the last one? 1, 3, and 6. Yep. Since h prime, which equals f, changes from what to what? Give me the first one that it does. Yeah, decreasing to increasing. I like to give the first one and then say vice versa. Changes from decreasing to increasing and vice versa. Don't say the word or, say and vice versa at those specific x values. What do you guys think? All right, guys. All we're doing today is practicing. So let me pass out the handout. You can turn it in tomorrow on Canvas or, but I would prefer it today.